Welcome to our fourth session of Managing Strategic Resources and Operations. My name is Dr. Razak Barry. I am the subject coordinator of this unit. In this session, we're going to talk about process analysis and resource utilization. The learning objective of this session is to be able to describe how to compute resource utilization and use of some of the equations, be able to identify process bottlenecks and some calculation of the throughput, explain how to apply little O to process analysis, understand the key concept and mathematics of the waiting lines, explain how simulation can be used to model queues and evaluate the performance, and also we will go through explaining the principle and logic of theory of constraint. Resource utilization refers to the measure of how effectively a workstation or individual is being utilized over an extended period of time. It represents the fraction or percentage of time that the resource is actively engaged in producing or productive work. Attaining 100% utilization is typically challenging in practice due to many factors such as machine changeover, delays, other operational inefficiencies. In job shops, where different types of jobs are processed with frequent changes and interruptions, resource utilization typically range from 60 to 95%. This variability is due to the need for adjusting machines and accommodating different job requirements. Flow shops, which have a more streamlined product flow, generally exhibit higher resource utilization. In such setups, where the production process follows a fixed sequence of operations, resource utilization typically falls within the range of 80 to 95%. The improved efficiency primarily distributed to reduce changeover and smoother workflow. In continuous flow process, where materials or product move continuously without interruptions, resource utilization tend to be even higher, often higher than 95%. The continuous flow nature of this process allow equipment to be more consistently and fully utilized, minimizing idle time and maximizing overall efficiency. So overall, resource utilization serves as an important metric to assess the efficiency and productivity of a workstation or individual, with high utilization indicating better utilization of resources and improved operational performance. So there are two ways to compute the resource utilization. Let's have a look at the top equations. The top equation computes utilization as the proportion of available resources that are being used. On the other hand, the bottom equation computes utilization based on the ratio of the demand rate to effective service capacity based on the service rate and the number of the service. So you can see the differences between these two equations. Now let's have a look at the throughput definition and meaning. Basically, it is means to the rate at which units or tasks are completed within a given time frame in a process. It is a measure of overall productivity and efficiency of a process. The unit of measurements of the throughput can be very dependent on the context, such as parts per day in manufacturing setting, transaction per minute in a software application, or customer per hour in a service-oriented environment. So the concept of throughput is concerned with the quantity of output generated by a process within a specific time frame. It indicates how effectively the process is able to deliver its intended output. A higher throughput signifies that more units or tasks are being completed within the given time period, indicating greater efficiency. So, when evaluating a process, it is important to consider the potential throughput that can be achieved. This involves assessing the process's capacity to handle and complete tasks, identifying potential bottleneck or constraints that might limit throughput, and optimizing the process to maximize output. By focusing on improving throughput, organization can enhance their productivity, meet customer demands more effectively, and achieve higher overall performance. A bottleneck refers to a specific work activity or component within the process that restricts or limits the overall throughput or capacity of the entire process. It acts as a constraint, preventing the process from operating at the maximum potential or achieving high level of productivity. Identifying and addressing bottlenecks is a critical aspect of a process design and improvement. By identifying the specific activity or component that is causing the slowdown or limiting the output, organization can focus the effort on resolving or optimizing that particular bottleneck. This can involve relocating resources or reallocating resources, streamlining the workflow, upgrading equipment, or implementing process changes to alleviate these constraints. Breaking bottlenecks is important because they hinder the overall efficiency and effectiveness of the process. By eliminating or mitigating bottlenecks, organization can enhance throughput, improve productivity, reduce the cycle time, and increase the capacity to meet the customer demand more effectively. Efficiently managing bottlenecks require a throughout understanding of the process flow, carefully analyzing of the performance metrics, and continuously monitoring and improving. By addressing the bottleneck, organization can optimize the process where they can increase overall output and also they can achieve better operational performance. At any moment, people, orders, job documents, money, and other entities that flow through processes are in various stages of completion and may be waiting in a queues. Let's have a look at flow time. Is the average time it takes to complete one cycle of a process. Okay, so it depends on actual time to perform the task required and how many other entities are in the working process stage. Little's law is a fundamental equation that establishes a relationship between flow time, throughput, and work in process in a system. It's named after John D.C. Little, who introduced the law in the field of operation research. The equation here states that the average number of units in a system working process is equal to the average throughput or multiplied by the average flow time, T, for each unit. So mathematically, you can see it can express as WRP equal to R times T. Little law holds true for various type of system, including manufacturing processes, system, service operation, and computer systems. It provides a valuable insight into relationship between flow time, throughput, and working process, allowing for performance analysis and optimizing of processes. By understanding the little laws, organization can make informed decisions regarding resource allocation, capacity planning, and process improvement. It helps in balancing working process levels, managing flow time, and optimizing throughput to enhance the overall efficiency and performance of the system. A queue refers to a waiting line where entities such as a job, task, or customer wait for a processing or service. Queues are commonly encountered in both manufacturing and service processes, particularly when it is uncertainty in demand and a service rate. I think we all stay in the queues, we all understand the queue lines. Now, let's have a look at in two processes. One is in manufacturing processes. Jobs or tasks often need to wait in queues before they can be processed at machines or workstation. This happens when there is a limited capacity to handle all the incoming job simultaneously. Jobs are typically prioritized and placed in a queue until machine or workstation become available for the processing. In the service-oriented environment, queues are prevalent in various establishments like banks, grocery store, restaurants, and other service providers that we can name lots of different examples. Customer waiting queues until they can be served by the available service personnel or resources. The length and speed of the queue can be influenced by factors such as customer arrival rate, service rate, and the number of service providers. Queues serve as a way to manage the flow and balance the demand and capacity within the system. They allow for structure and organized handling of entities, ensuring fairness and efficiency in the process of service deliveries. However, excessive waiting time in queues can lead to customer dissatisfaction, reduced productivity, and bottlenecks within the process. Effective queue management strategy involve analyzing and optimizing factors such as queue length, wait time, service rate, and resource allocation. By understanding and addressing the dynamic of the queues, organization can improve customer experience, enhance operational efficiency, and better manage the uncertainty associated with demands and service rates. So there are three common queuing configurations. One or more parallel services fed by a single queue, several parallel servers fed by their own queues, and a combination of several queues in the series. Let's have a look at one of those examples that we mentioned. So in A, which is the left side, is when there is one line for queuing and there are like three servers, like a post office, right? When we go to a post office, we always stand in one line, but there are multiple people serving. Or in the B, which is on the right side, when several power services are fed by their own queues. It's commonly in supermarkets, right? When we go grocery shopping, you can see there might be different places that we can go and stay in a queue, and we just serve by that person. Queuing theory is a branch of mathematics that focuses on analytical study of waiting lines or queues. It provides a framework for understanding and predicting the behavior of queues in various systems such as manufacturing services or processes, service operation, telecommunication, and computer networks. Queuing theory enables the calculation and analysis of various performance measures related to waiting line. Some of the common performance measure computer using the queuing theory like probability of empty system is referred to likelihood that both the queue and the server or service facility are empty. For example, there are no units waiting for service. Average number of units in a queue it represents the average number of unit or customer waiting in a queue for service. Average number of units in the system. This measure includes both the unit waiting in the queues and those currently being served. It provides the average number of units present in the entire system. Average waiting time in a queue represents the average amount of time or unit or customer spent waiting in a queue before being served. Average time in a system, this measure encompasses both the waiting time in the queue and the actual service time. It provides the average total time a unit spent in the entire system. Then beyond probability of waiting, it denotes the probability that an arriving unit or customer has to wait in a queue before receiving the service. And also we have probability of the units. In the system, the measure focuses on the probability of having a specific number of a unit present in the system, including both queue and the service facility. By applying queuing theory, organization can gain insight into the performance characteristics of the system, make informed decisions regarding resource allocation, optimize service level, and manage waiting times to enhance customer satisfaction and overall of the operational efficiency. The theory of constraint (TOC) is a management philosophy and methodology that aim to improve overall process throughput by identifying and optimizing the constraint or bottleneck within a system. It provides a systematic approach to maximizing the utilization of bottleneck work activities and workstation to increase overall productivity and achieve organizational goals. The TOC philosophy recognizes that a constraint is anything that prevents an organization from moving closer to or achieving its objective. Constraint can be physical or non-physical in nature. Constraint can or are associated with the capacity of a resource such as machines, employees, workstations. These constraints create bottlenecks in the process flow, limiting the overall throughput of the system. Identifying and addressing these physical constraints is crucial in improving the overall performance. So we already mentioned one type of the constraint, which is a physical. The other type is non-physical constraints in TOC are typically environmental and organizational factors that hinder the system ability to achieve its goals. Examples of non-physical constraints include low product demand, inefficient management policies or procedures, and or inadequate communication channel. These constraints need to be identified and resolved to optimize the system performance. The TOC methodology involves a systematic process of identifying constraints, exploiting them by maximizing the utilization, and then elevating or removing them to further improve the system throughput. This iterative approach helps the organization continually optimize the process and align them with overall business objectives. By applying the principle of TOC, organization can gain a deeper understanding of demand and capacity management, identifying and overcome process bottlenecks, improve resource allocation, and ultimately increase the overall productivity and efficiency. So you can see this is the overview of a basic principle of TOC, where we have non-bottleneck management principle and we have a bottleneck management principle here. In conclusion, utilization, throughput, queuing model, and the theory of constraint TOC all play crucial roles in understanding and improving process efficiency and performance. Utilization measures the fraction of time a workplace or workstation or individual is busy, and while achieving 100% utilization is challenging. Optimizing utilization level within job shops and continuous flow process can lead to improved productivity. Throughput represents the rate at which units or tasks are completed in a process. Monitoring and maximizing throughput can help organizations increase the productivity and meet customer demands more effectively. Understanding queuing model allow manager to analyze waiting lines, optimize resource allocation, and minimize waiting times. By implementing strategies to reduce queue length and wait time, organization can save time, costs, and enhance customer satisfaction. Then we talk about the theory of the constraints that provide valuable principle and a systematic approach to identify and address constraints that limit overall system performance. By focusing on the most crucial or critical constraint and optimizing the utilization, organization can improve the demand and capacity management to achieve the overall goal. By leveraging all these concepts and methodology, manager can gain insight, make informed decision, and implement improved that optimized processes, save resources, and enhance customer service. And we reached to the end of the session today. I hope you enjoyed this session, and I wish you all the best and good luck.